Yes, hello everybody. This is my video based on forces over Coulomb's law. How we can check to solve the problems based on Coulomb's law. Means we learn how to apply Coulomb's force concept over the problems and numericals based on that. Let's see. I'm going to discuss some questions here and then I will solve those questions and that will explain that how we apply the concepts of electrostatic force or Coulomb's law over the problem. See here. See, there are two charges, both are positive, Q and Q. So there are two charges, one is positive and there is also positive here. And they are separated at a distance or they are hanging the string from the ceiling. And these two strings are balanced here over this position. So there is something which is balancing. These two charges at a separation are and the strings are in this position. This is called the equilibrium position of the strings. So which force is responsible to keep it balanced? That is Fe, Coulomb's force. So my job is here to calculate the variable parameters in this question and how we analyze this type of questions. See here. Now come over only one side because whatever we do here, we do the same thing to that side of the problem. So look only one portion of the question. See, mg, mass of the charge is downward. This is the tension here. So there are two components of tension, that is T cos theta and this will be T sin theta. So here, checking only one portion of the question, I can solve it like this. That will be T cos theta is equals to
Don't write there. It's not visible. After the part is equal to.
Okay, that's minor thing they can notice.
No, that's the light, this part of light.
Yeah. T cos theta is equals to mc under the balancing condition.
You need to write mg, don't worry, it's still not visible in the video. That point, circle the point. Don't.
T cos theta is equals to mc. It's still over the dark.
It's slightly down.
Slightly, then that can be adjustable. They can understand that it's mc.
Yeah.
T cos theta is equals to mc, and T sin theta is equals to the repulsive force here under the balanced condition. Whenever the setup is balanced, in that case we can do that. So by simple arrangement from equation 1 from equation 2, so we have tan theta is equals to Fe by mg and we have T is equals to under root mg square plus Fe square. So mg plus Fe square. So you can get, don't do this. This is making shadow over the screen. Don't do, let it, that's my problem here. So we can find T, the tension along this string, and the angle of this string making it the vertical of the ceiling. So that will be this by solving first and second equations here. This is very simple case. Now there's probability of developing a complex question in this type of problem that I'm going to analyze here. Now let me do. So I'm coming to the same setup right now. So this is Q again plus Q. So if someone says that the charge is leaking by dq by dt, means these two charges are leaking by constant rate. So the condition will be that the charges Q leaking, charges Q are leaking by dq by dt, a constant rate. So what will be our reaction? So first I will do qualitative analysis, then I do quantitative analysis of what happens in the question. See here, within the qualitative analysis, so if here the magnitude of Q here and here both are reducing by some sort of factor, that is dq by dt, and it's a constant rate, so in that case dq by dt here, so this both amount of charges are reducing by time, so the force will decrease, so repulsive force will decrease by some amount. So repulsive force will decrease. So once repulsive force will decrease, then T sine theta will be effective, and then the charges rushing towards each other. In that case, this angle will be smaller, and if this angle will be smaller, then T sine theta, if they're coming towards each other, then this angle will be smaller, and then T sine theta will be smaller, so that T sine theta can balance Fe. That T sine theta can balance Fe. So that F is also reducing, T sine theta is also reducing, because we are getting that as the force is reducing here, the charges are rushing towards each other, and in that case this angle will be smaller, and as angle will be smaller, this factor will be smaller too. So they are always balanced. T sine theta is balancing Fe always. Now come here, what happens? If this angle is going to be smaller, so T cos theta will be bigger, and in that case T cos theta will be greater than mg, because as Q is reducing by dq by dt, in that case its mass is also reducing, so mass is also reducing. If mass is reducing, so this force is also reducing. But here I'm checking that as angle is going to be smaller, this angle becomes smaller, and this factor will increasing. So our conclusion by the qualitative analysis is that here, that T sine theta is always equals to Fe under the leaking condition, under the leaking of charge. That leaking, my spelling is wrong. It's that leaking, it's this leaking. Sorry for it.
What happened now?
What happened? Under the leaking charge. So this
Our internal memory has failed. This is but the video is still on.
T cos theta is equals to not, okay? See, that's our conclusion by qualitative analysis, that T cos theta is increasing here, because as angle is going to be smaller, so this will be smaller, and this angle will be smaller, so the value increases here. And once the value is increasing here, this mg is going to be smaller, so this will be T cos theta is going to increase. But mg is decreasing, because if charge leaking, so mass is also leaking. But here, T sine theta is balanced by Fe. So you can say that this is going up, but not. So here a factor is tension. So once I consider the variation here and here, then the value of tension will be such that from the previous analysis, that T square is equals to mg square plus Fe square. From that analysis, this is always balanced. So we can take one situation that cos theta is increasing, but the factor T is decreasing. So this section, if this section is balanced or about to balance under the leaking of charge conditions. So this will, we think that this is increasing, but there's a case that this is balanced, and so we'll have to deal this question under this condition. d cos theta is equals to mg. In that case, they are always balanced and the charge is rushing towards each other. So the forces are balanced here also, so they have no acceleration, they just rush towards each other by constant velocity. So I'll have to find that velocity in terms of distance. So my job is done here. Now I'm going to analyze that question. Let me to raise some portion of this question.
At the position only D in the condition is under the circle.
So see here, what we are going to do, that is T sine theta is equals to, that is T sine theta is equals to Fe. So 1 by 4 pi epsilon naught q squared by x squared. Suppose I have taken the distance now here. So not x, I am still taking it in terms of r. So r square. Understood?
Yeah, it's visible.
R square. And as we have seen that why I have written this, because what? Once we know, as we know that if the charges are rushing towards each other by the leaking of charge, then angle becomes smaller, and once angle becomes smaller, we can convert sine theta into theta. Theta when theta is very, very small. So this is our conclusion or our analysis here. Now come over here. So this,
Why don't you switch the face?
no, let me to complete this section first. So from there, this is our setup, and I can use it. And I can make the analysis that we have to solve this problem over this concept under the balance condition, because we know that cos theta is increasing, but the t is the variable which is dependent on cos and sine both. So t is decreasing and cos is increasing. So this factor remains equal to mc. And at very small angle, we can write for this one, that is mg. So cos theta is equals to 1 when theta is very, very small. Very, very small. So we have the value t is equals to mc here. And put this value t equals to mc in this equation from here to this. So we have a complexity. So I'm going to erase this now. So you have seen here that we have t theta is equals to this by converting sine theta into theta, but theta is very, very small. We have t cos theta is equals to mc by our previous analysis, what we have done before starting the quantitative analysis in our qualitative analysis. So we get t equals to mc here. Now I'm going to put this t equals to mc in this portion, and I'll solve the questions for the velocity of the charges rushing towards each other. Let me erase this portion because my board is short. I have plans to increase my board in my recording room, but now I'll have to manage these things with these boards and with these rooms.
Why can't you face it?
Wait, don't worry. Let me complete this. T theta is equals to this. So this is mc theta, as we know, q squared by 4 pi epsilon naught. As we have discussed t equals to mc, similarly I put that value and I'm getting this. Now come here. That is q q square is equals to mg theta 4 pi epsilon naught r square. So my job is to convert. One more thing here, see, as angle will be very small there, as we have done in our previous section. mg r by 2 by r by 2 by l. That is the length of the string. Yes, that is 4 pi epsilon naught r square. That is this is l, this is r by 2. So theta is, you see here I have replaced this theta by r by 2 by l. So come in our figure, our initial figure, that this is the ceiling, the charge is hanging here by a string, the length of the string is L, and it is at a distance r by 2 from center of the separation to add the charge. So this is theta. So if theta is very small, you can replace this theta by r by 2 by L. So I have done that. So we get this equation here. Now I'm erasing some upper portion of the solution so that I need more space, because I have shortage of space. See, q square is this, so come over here. That will be q square is equals to mg
4
by 2l r cube by 4 pi epsilon naught. So, and you can see that there are all these things are constant. So I can write it as a CRQ, where C is a constant.
4 pi epsilon naught will be upstairs.
Yes, sorry, this is upstairs, 4 pi epsilon naught.
Write it just closer to
Yes. So this comes over there. So that and the CRQ, C is a constant, and the value of C is equals to this total constant. So Q squared. There's one question you can ask me, that M is also leaking. If the charge is leaking, then M is also leaking. So why I can take C is equals to constant over this? And the leaking of charge is considerable for the electrostatic force and Coulomb's force, but the leaking in mass is very negligible, as we are aware of quantization of charge. In that case, we can say that the reduction in charge has negligible effect over the mass. That's why we have to take it almost constant. But in hyperphysics, in quantum electrodynamics, this leaking should be taken in care. So come over here, this. Now I need to differentiate it. Let me to make more space. C. That is be by differentiating with respect to time to the both sides. Time to the both sides. That will be 2q dq by dt is equals to C3 r square and dr by dt. So this 2x q square x square and this so 3r squared dr by dt. Now this term is a constant leaking, so we can treat it as a next constant. So this will be c dash and c 3 r squared dr by dt. So from here we can replace this q from here. So the value of q will be 2 into c power 1 by 2 or power 3 by 2. That will be 3c r square, and this term gives us the velocity of the charges in towards each other. So we can write this way. Is equals to, and I'll have to find this value proportional to what. So this is constant, and this constant. So I need more space, so I need to erase some. See here, come over here, from here to here. That will be 2y3 c dash. There is one more constant here, this is also here, c dash, and c power 1 by 2, that is c, and r square, and r power 3 by 2, that is v. So therefore v is equals to, this whole becomes one constant. So I can write this, that is r power minus 1 by 2. So this constant comes for all these things. These are also a constant. This whole term is a constant. So I can replace this whole constant by this constant and subtract this, we get this. So what we got here?
There will be r power 1 by 2.
No, there will be not r power 1 by 2. This is something, this is a downstairs, this is there. So v is equals to this. So what we get here? That the velocity of the resting charges proportional to the distance, inversely power minus 2. V proportional to r power minus 2. That is our conclusion here. So we have solved this question, and you can ask me that I have sources of space, I have sources of some good quality videos. So I got here, and there are a lot of sweats over my face, so that is due to I'll have to off the fan to shoot this video. So let me to take a break, then I start. So stop it, don't cut it, just stop the recording. So that will start from this section.
From where will you
With that red point, hold it.